Good evening, everyone. I am starting my class right now because no one has joined, but I still have to take this session and upload it on YouTube. So I'll be discussing the questions as I do every week. Okay, I think someone has joined. Hello, Krishna Mohan. Am I audible? Sorry. Hello, Krishna Mohan. Hello, Krishna Mohan. Am I audible? Hello, Mohan. अच्छा, हम आपको 7 बजे के बाद कॉल करते हैं। वो थोड़ा क्लास में है, ठीक है? Am I audible, Shakir?
Yes, sir.
Yeah. Is the PPT visible?
Yes, sir, it's visible.
Okay. So I had started the class before you all joined, since I had to take the live session and upload it on YouTube. But since you have joined right now, I'll be starting
Yes,
it
sir.
right away. Uh, Before starting, I would say that you know the syllabus, right? You know the syllabus of this geotechnical engineering. You have the
Yes,
syllabus
sir.
with you, right? So in this 8th week, you have flow nets, isn't it? You have
Yes, sir.
flow nets and stresses in soil from surface loads, isn't it?
Yes, sir.
Now in flow nets, I guess I had discussed flow nets in a previous class in seepage analysis, right? Flow through soils. So some part of flow nets I had discussed, isn't it, Shakir?
Yes, sir.
Yes, and stresses in soil from surface loads. I guess Boussinesq theory is a main part of this chapter. I think you have learned Boussinesq theory, right? Boussinesq theory, Westergaard's
Yes,
theory.
yes, sir.
Yes, so Boussinesq theory is a main part of this chapter. Without the Boussinesq theory, the stresses in soil is incomplete, isn't it? But
Yes, sir.
according to the syllabus, this stress distribution, this chapter, it has been divided into three parts. The first part is here in week 8 with flow net stresses in soil from surface loads. The second part is in the next week, Boussinesq theory. Okay, and the third part is in the next to next week, Newmark's chart. Okay, so I am in this week in this content. I'll just be clear with you what I have included in this. I could not incorporate many numericals because majority of the numericals of stress distribution is with the Boussinesq theory. Okay,
Yes, sir.
so leaving out Boussinesq theory and Newmark's chart, whatever numerical I could get, I could incorporate, and the rest numerical I have incorporated from the flow nets chapter. Okay, different
Yes,
numericals,
sir.
not the one you have done. Some different numericals. Only the next week, Boussinesq theory, the chapter Boussinesq theory means the next week's live session will be purely based on numericals. Okay, Boussinesq theory.
Yes, sir.
Clear? Okay. So I guess we can start right now.
Yes, sir.
No doubt. Okay. So good evening, everyone. This is the eighth live discussion of Geotechnical Engineering One, and the topic today's um, topic of discussion is flow nets and stresses in soil from surface loads. Okay. So the first question is okay. As per the rules, I'll be discussing the questions, and then I'll be giving you some time. You will solve them and then I'll be discussing the answers. Okay. The first question is, stresses due to self weight are also known as. Stresses due to self weight are also known as. The options are static stresses, gravity loads, geostatic stresses, effective stresses. Okay, this is the first question for those of you who have joined late. I'll repeat the question. Stresses due to self weight are also known as. The options are static stresses, gravity loads, geostatic stresses, effective stresses. Just a minute. 6 minutes. Okay. Next question. Contour joining points of equal vertical pressure below the ground is called. Contour joining points of equal vertical pressure below the ground is called. The options are isohyet, isobar, isochrone, or none of these. Contour joining points of equal vertical pressure below the ground is called isohyet, isobar, isochrone, none of these. Next question. The Poisson's ratio for elastic materials varies between. The Poisson's ratio for elastic materials varies between. The options are 1 to 2, 0 to 1, 0 to 0.5, 0.5 to 1. Somebody's mic is on, I guess. Ashok, I think your mic is on. Please mute yourself. Yeah, the Poisson's ratio for elastic materials varies between 1 to 2, 0 to 1, 0 to 0.5, 0.5 to 1. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. The options are 1.22, 0.86, 0, 1.62. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. The options are 1.22, 0.86, 0, 1.62. Next question. Which one among the following is a scalar function of space and time whose partial derivative with respect to any direction gives the velocity component perpendicular to the original direction? I repeat, which one among the following is a scalar function of space and time whose partial derivative with respect to any direction gives the velocity component perpendicular to the original direction? The options are stream function, scalar velocity, potential function, or velocity potential. I repeat the question. Which one among the following is a scalar function of space and time whose partial derivative with respect to any direction gives the velocity component perpendicular to the original direction? The options are stream function, scalar velocity, potential function, velocity potential. Is this question clear? Is this question clear? In doubt? Anyone?
No, sir.
Okay. Next question. Westergaard's formula for vertical stress gives greater value of stress than that by the Bosnius formula when R by Z exceeds. I repeat, Westergaard's formula for vertical stress gives greater value of stress than that by the Bosnius formula when R by Z exceeds. The options are 1.12, 1.52, 2.22, 2.62. Westergaard's formula for vertical stress gives greater value of stress than that by the Bosnius formula when R by Z exceeds 1.12, 1.52, 2.22, 2.62. Next question. The zone within a soil mass bounded by a contour of constant vertical pressure intensity is called. The zone within a soil mass bounded by a contour of constant vertical pressure intensity is called. The options are stress zone, pressure bulb, stress bulb, none of these. I repeat the question. The zone within a soil mass bounded by a contour of constant vertical pressure intensity is called. The options are stress zone, pressure bulb, stress bulb, none of these. Next question. A combination of velocity potential and stream function is called. A combination of velocity potential and stream function is called combined function, stream velocity potential, complex potential, or none of these. A combination of velocity potential and stream function is called combined function, stream velocity potential, complex potential, none of these. Next question. In the case of anisotropic soils, the flow net is drawn for the transformed section, which is obtained by reducing the horizontal dimensions and keeping the vertical dimensions unchanged. Is this statement true or false? In the case of anisotropic soil, the flow net is drawn for the transformed section is obtained by reducing the horizontal dimensions and keeping the vertical dimensions unchanged. Is this statement true or false? Next question. A stress theory suitable for stratified soil is. A stress theory suitable for stratified soil is. Boussinesq theory, Newmark's chart, Westergaard's theory, none of these. A stress theory suitable for stratified soil is Boussinesq theory, Newmark's chart, Westergaard's theory, none of these. Next question. The shape of a field is approximately a. The shape of a field is approximately a rectangle, square, rhombus, or hexagon. The shape of a field is approximately a rectangle, or square, or rhombus, or hexagon. What is a field? You know, I think. Shakir,
The area between the two adjacent stream stream function.
what? Two adjacent what? Write in the chat box. Your mic is not working. Okay, it is the area between two adjacent flow lines and two adjacent equipotential lines. That is a field. And a field, the shape of a field is approximately a rectangle or a square, a rhombus or a hexagon.
Rhombus.
No need to say now. You will get time to solve the questions. Okay.
Square and rhombus.
You just write down the answers. I'll give you time to solve all the questions. After that, we'll discuss. Okay. Okay. Again, a true or false. Quantity of water flowing through each flow channel is the same. True or false? The quantity of water flowing through each flow channel is the same.
Sir, quantity of water flow मतलब discharge.
Discharge, yeah. Discharge through each flow channel. Quantity of water, if you divide by time, you get the discharge. Okay. So if the quantity is same, the discharge is same. So quantity of water flowing through each flow channel is the same. True or false? Next question. The Westergaard's influence factor is a function of. The Westergaard's influence factor is a function of R, Z, both of these, none of these. The Westergaard's influence factor is a function of R. R means the radial distance from the point of load action. Z is the depth till which we are calculating the stress. Both of these or none of these. Okay. Don't tell the answer now. Okay. Next question. From this one onwards, I guess, yeah, only numerical. Okay. Okay. First, draw this diagram and then tell me if you have drawn it. water tank is supported by a ring foundation. The diameter is given. Outer one is 10, inner one is 7.5. Have you drawn the diagram? Have you seen such kind of water tanks with ring foundation? Anyone?
No, sir.
Okay. Overhead tank, they have this kind of ring foundation. Okay, and in this sum, you have to calculate the vertical stress at a depth of 4 meter below the center of the ring foundation. Means at the center of the foundation, at this point, at a depth of 4 meter, you have to find out the vertical stress. Given that the uniform load intensity of this ring foundation, that is the shaded area, is 160 kilonewton per meter square. This is the this is the UDL transmitted by the foundation, and the outer diameter is 10 meter, inner diameter is 7.5 meter. So now, if this ring foundation transmits a UDL of 160 kN per meter square, then following the Westergaard's analysis, taking Poisson's ratio as 0, yes, it is important, take Poisson's ratio as 0, compute the vertical stress induced at a depth of 4 meter below the center of the ring foundation. Clear? Is it clear? Any doubt?
Yes, sir.
Clear, right?
Yes, sir.
Okay. So after this, I'll go to the next question then. Okay. An earthen dam rests on an impervious foundation. The relevant data is given below. Height 58, freeboard 1.5, upstream slope 2.75 is to 1, downstream slope is 2.5 is to 1, crest width is 6 meter, and length of the drainage blanket is 110 meter. Coefficient of permeability of the dam material is kx in the horizontal relation is 4.5 10 to the power minus 7 meter per second, and ky 2 10 to the power minus 7 meter per second. Determine the seepage to the earthen dam. Have you done this kind of sums? Have you
No, sir.
solved any
First time.
question? Okay, first time. Okay, do you know this? I'm telling you about the length of the drainage blanket and all. Do you know the parts of the dam and how to solve this question?
No, sir.
Okay, just a minute. I'll just try to draw the diagram. I thought of drawing the diagram, but I thought I might know this. Just a moment.
Sir, in this question, number of alumni in potential line.
Number of flow lines you don't need. Actually, there's a different formula for this. Okay, when you are calculating that of an earthen dam, I'll just tell you those things which you don't know, because height of the dam you can find. You know what is the height of the dam, what is the freeboard, you know. Upstream and downstream, the slope is given. That is also given to you. Crest width, I guess you know what is the crest width is. Length of drainage blanket, I think you don't know. And permeability of the embankment material. Basically this is an anisotropic material. Okay, that's why this has kx and ky differently, separately. So here the permeability q is, the formula is not kh in kh into nf by nd. It has a different formula. Okay, so if you see, this is an earthen dam. This is the base material, and this is the earthen dam. Okay, and this is the height of the dam. Suppose the water is still here. Okay, then this is the freeboard. Okay, now there will be a certain point called C over here, up till which there will be a phreatic line, topmost phreatic line. It will be like this, and then it will come down at this level. From this level till this level, from this here to here, this is called the drainage blanket. Okay, and this is the crest width, that is equal to 6 meter. Yes, that is equal to 6 meter. Drainage blanket is given over here, 110. This is the upstream side. This is the upstream side. This is the downstream side. Okay, this is the downstream side. Crest width drainage blanket, height is 58. Overall height 58 meter, and kx and ky is given. So it has a formula and it has a technique. So the formula, you know how to calculate this sum using the formula k into s. What is s? You know what is s? You don't. Yes. Do you know, yes or no? Hello.
No, sir.
Okay, you just write it down. Draw this diagram. Just write down the height and weight and everything. We'll discuss it in here. Over? Is it over?
No, sir. 1 minute.
Yes. Write down the.
Sir, is this question from topic seepage theory?
Yes, from flow nets, from the topic that seepage analysis. You first write down the question. Okay, there is a derivation of the particular formula which is being used for this for solving this sum. That you can check any standard textbook, you can get it. I will tell you the solution. Okay, no worries. You tell me if you have finished writing down the question.
Yes, sir. Company.
Okay, so we'll discuss this question. No worries. Next question. A concentrated load of 200 kilonewton acts at the ground surface. Find the intensity of the vertical pressure at a depth of 10 meter below the ground surface and situated at the axis of loading. So when there is a concentrated load of 200 kilonewton, the ground surface, intensity of vertical pressure, depth of 10 meter below the ground surface at the loading axis. This is the first part. And second part is find the vertical pressure at depth of 5 meter and distance of 2 meter from the loading axis. Same load, same kind of load, concentrated load. Now you have to find out the pressure, depth of 5 meter and distance of 2 meter from the axis, means radial distance is 2 meter. Okay. Over.
Yes, sir.
Okay, right. Over. What, yes or no?
No, sir.
Okay, okay, right, right. Are you done?
Yes, sir.
Okay. Next question. The base dimensions of a flow net are 4 meter and 3 meter for natural and transformed sections, respectively. What is the anisotropy ratio? Do you know what is anisotropy ratio? Hello? Do you know what anisotropy ratio is?
No, sir.
No, sir.
You don't know. Okay. So basically, in this sum of the dam, I have said na coefficient is different in different direction. In the x direction, k is 4.5 and y direction k is 2. That means the material is anisotropic. It has different properties in different direction. So in
Okay,
this case,
finding of k is that root of kx to ky.
root of kx to ky, that is used, but anisotropy ratio is basically the ratio of the this coefficient k, ratio of this k in the x-axis to that of the y-axis. Kx by ky is the anisotropy ratio. Okay.
Okay.
So if the base dimension is this for natural and transformed section, respectively, what is the anisotropy ratio? Okay. Clear? Is this question clear?
Yes, sir.
Okay. Next question. I think this is the last question. Yes. For a sheet pile wall constructed in a soil having effective grain size 0.1 millimeter, the difference of the upstream and downstream water levels is 3 meter. If the flow net drawn for the problem yields 2 as a ratio of number of head drops to the number of flow channels, then what is the discharge in unit of meter cube per second per meter length of sheet pile wall?
Permeability.
Hello? Yes, yes. Any doubt?
Permeability in this question.
Yes. that is not given, you have to find it out using the grain size. You know the formula with probability and grain size, right? There is a formula. You try to find it out. Grain size or whatever data you have, you just find it out.
Question is over, sir.
Okay, done.
Done, sir.
Okay, so you all solve these questions right now. Okay, I'm giving you time around 15 minutes. I'll start at 6:05. Okay, is it okay?
Okay, sir.
Or you need more time
Yes,
to
sir.
solve the question? You try to solve this question. See, this is the question. You try to solve this question by your own way. Okay, then we'll discuss. Okay, I guess you can solve all the other questions, but since you don't know this, after you finish the other questions, try to solve it within if you have time. I'll start at 6:05. Okay,
Yes, sir.
is it okay? Okay, everyone, you solve this. I'm giving you time. Hello. Have you solved the questions? Hello.
Yes, sir.
Okay. Others? Ashok, have you solved the questions? Okay. All right. The PPT is visible, right?
Yes, sir.
Okay. So just start. Just follow up. Okay. Stresses due to self weight are also known as. What is the answer?
Geostatic stresses.
Yes. Use the stresses. Gravity loads are a general term for defining loads which act due to gravity, but it is not specifically self weight. I mean, there can be a ground where buildings have been built and the gravity loads might be acting on them, but that is not because of self weight. So, geostatic stress is a body's self weight that is acting because of gravity. Good. Stresses due to self weight, also known as geostatic stresses. Yes. I believe you know what effective stress is, Shakir.
Yes. Yes, sir. It's a different stress and forward.
Yes, total stress and pore water stress. If we find out the difference, that will give us the effective stress, right? Yes. Next question: contour joining points of equal vertical pressure below the ground is called. Easy question.
Isobar.
Isobar. Yes.
Isobar develop same or different.
Yes.
Is isobar and same or different, sir?
Isobar and what?
And citrus bulb.
No, bulb is a different thing. Isobar, iso means similar, same. That is a contour. When you say bulb, a bulb means it is defining a region, okay,
Yes,
and
sir.
not
Region.
not not a, not it is not connecting points. So isobar, okay. I'm coming to some. I gave you a question right about pressure bulb and
Yes,
all
sir.
those statics. I'll be coming to that. Okay, wait.
Okay.
Yes, so contour joining points of equal vertical pressure below the ground is called an isobar. Yes. The Poisson's ratio for elastic materials varies between. What is the answer?
So 0 to 0.5.
Yes, 0 to 0.5. And why Poisson's ratio was incorporated here? Because in the Westergaard formula, you have Poisson's ratio, right? For finding out the value of eta. Do you remember in the formula for Westergaard's stress formula? You have the value of eta, right? 1 by 2 pi eta square.
Yes, sir.
Yes, so that part has the Poisson's ratio. So stress is also dependent upon the Poisson's ratio as per Westergaard analysis. And for elastic materials, this property, this Poisson's ratio varies from 0 to 0.5. Yes, good. The intensity of radial shear stress in ton per meter square at a 0.4 meter directly below a 2 tons point load is. What is the answer?
I didn't get this question.
It is a tricky question. See, I am calculating the intensity of stress at a 0.4 meter directly below. If it is
Yes, sir.
directly below the point of application of load, then the radial distance is how much? 0, right? So will there be any radial shear stress or there will be only normal stress? I'm applying load over here like this. This is the ground. I'm
Oh, yes,
I'm
sir.
talking about 4 meter at this point. This is the point, suppose P. So will at this point will there be any shear stress or
No,
only
sir.
normal
Only normal.
stress? So
Yes, sir.
the intensity of radial shear stress is how much? Zero.
Zero.
Understood?
Yes, sir.
Yes. So you have to see the question and understand the language properly, not only just jot down the data. Because you have 4 meter, you have 2 tons. Okay, but with that you can do nothing because I'm asking about radial shear stress and not normal stress. Okay, the shear stress will be 0. Okay, next question. Which among the following is a function, is a scalar function of space and time whose partial derivative with respect to the direction gives the velocity component perpendicular to the original direction?
It's a stream function.
Stream function, very good. Stream function, because stream function is xi, right? Stream function we represent it as xi. So if we partially differentiate xi with respect to y, del y, we will get, as per soil mechanics, we'll get velocity in the x direction. And if we differentiate xi with respect to x, we'll get velocity in the which direction? Y direction, but
Y
opposite
direction.
side. What is
Minus.
happening?
Yes, sir.
Yes, what is happening? In the y direction, this is the y direction, we are getting x positive. That means from here to here it is coming. Okay. Now, in this case, what is happening? If it is like this, we are doing it in this direction, differentiating. It is coming like this. Okay. So, it is differentiating and finding the velocity component perpendicular to the original direction in a clockwise direction, right? In a clockwise manner.
Yes, sir.
Okay, so I did not give the clockwise in the question, but it always does in a clockwise manner. Yes, so the answer is stream function. The partial derivative with respect to any direction gives the velocity component perpendicular to the original direction. Westergaard's formula for vertical stress gives greater value of stress than that by the Boussinesq formula. When R by Z exceeds, what is the answer?
1.52.
1 point. Hello.
1.52.
1.52, yes, because for the Bosing's analysis and the Westergaard analysis, Kw is throughout the given chart, Kw is less than Kb. It is only more than Kb after the R by Z value exceeds 1.52. Okay, good. Next question. A zone within a soil mass bounded by a contour of constant vertical pressure intensity is called?
Pressure bulb.
Yes,
Pressure bulb.
yes, and someone was asking about the difference in bulb and isobar. See, if here is the pressure, here is one same pressure. So suppose the pressure is P, okay, and these are the points which indicate the pressure P. So if I join all these points with an isobar, okay, zone in the soil mass bounded by a contour of constant vertical pressure. This contour of constant vertical pressure intensity is called isobar, and the zone within an isobar is called pressure bulb. Not stress bulb, but pressure bulb. Clear? Who was asking about the difference in bulb and isobar? The difference between bulb and isobar, Shaki, did you get disconnected?
Yes, sir.
could you understand the difference between bulb and isobar now?
No, sir.
Yes?
No, sir.
You got disconnected. Okay, see. Just a moment. Suppose within a soil mass, these are the points of equal vertical pressure. Okay, these are the points of equal vertical pressure. Now, if I join all these points like this, then this line is called an isobar, right? Isn't it?
Yes, sir.
And soil mass bounded by a contour of constant vertical pressure intensity. This contour of constant vertical pressure intensity is also called an isobar. So our zone in a soil mass bounded by an isobar is also called pressure bulb. Okay, clear? This is a bulb, it
Yes,
is a
sir.
zone,
Right.
and this zone is bounded by the isobar. Next question. A combination of velocity potential and stream function is called. A combination of velocity potential and stream function is called. What is the answer?
A complex potential.
Yes, complex potential. What is the formula for this?
Said
This is W.
dou square u by
W equals to velocity potential is phi, right?
yes, sir.
Phi plus I think I and xi. It is a complex function. That is called complex potential. Real
Yes,
value
sir.
and imaginary value combined
Values.
will give the complex potential. Clear? This is the combination of velocity potential and stream function. Right, complex potential. In the case of anisotropic soil, the flow net is drawn for the transformed section, which is obtained by reducing the horizontal dimensions and keeping the vertical dimensions unchanged. True or false? What is the answer? Anyone? Do you know the answer or you don't? Just tell me.
No, sir.
Yeah, okay. So what happens is, in the case of anisotropic soil, if there is a soil layer like this, we are finding out permeability. So in the case of quicksand, seepage, we can find out the flow in the upward direction. But in case of permeability, we generally find out the flow in the horizontal direction, right? How much can the soil flow through? How much can the water flow through the soil? So in this case, if it has different properties in different direction, it is called anisotropic soil. Now in this anisotropic soil, we can see that there is a value of kx and there is a value of ky, because in the x direction it has one particular value of permeability and it is different in the y direction. Now if we want to find out an equivalent, because it is crossing various y sections, right, having various different kind of ky values. So this equivalent value of kx will be equals to, or equivalent k will be equals to, this kx into, will be multiplying it with root over of ky by kx, and hence the equivalent k which we will be using for the numericals will be equal to, equivalent kx will be equals to how much? Root over of kx into ky.
KY.
Okay, so this kx, that is the horizontal dimension, is transformed using this ratio. Okay, and the vertical dimension is kept unchanged because we are in the process of calculating the amount of discharge. We don't need the transformed ky actually, right? So this statement is true. Clear?
Repeat once again, sir.
In the process of finding out the discharge, which value do you need? You need the horizontal value, right? Kx,
Yes,
because
sir.
equivalent k will be getting from kx. Now, because kx is passing through so many y layers, right? This is the y section, this is the y section, and at each and every y section it has a different value of permeability. So to transform this kx, I am trying to transform this anisotropic soil into an isotropic soil. Okay, so to find out the equivalent k for isotropic soil, or I'll not write kx, I'll just write k to make it simpler. In isotropic soil, it is only k, right? Not kx and ky, isn't it?
Yes, sir.
Yes. So this equivalent k will be equal to, since I am trying to find out the discharge along this direction, so I will be reducing this kx and transform this kx into equivalent k for isotropic soils, which is equal to kx into root over of ky by kx. Okay, and this is the value. This is an approximate value of the equivalent k had the soil been isotropic. Is it clear? Hello? If it is not clear,
Yes, sir. Yeah, sir. Done, sir.
okay. Okay. So this is the value of equivalent k. We are getting this by transforming the value of permeability coefficient in the horizontal dimensions. Okay. So this is true. Next question. A stress theory suitable for stratified soil is which one?
Westergaard.
Yes,
Westergaard story.
Westergaard is useful for stratified soils and warped clay. I discussed in the first day. Those kind of soils, Westergaard's theory is more suitable. It consists of more number of parameters, I believe. That is why it is more suitable for stratified soil. Yes. Sheffield is approximately a,
Yes.
yes. If these are the two flow lines and this is the two equipotential lines, it might look like a rhombus because the flow line is curved, but had the flow line been straight, we consider this flow line to be straight, it is a square. Okay, so square will be the answer. This is a field, right? This is flow lines, this is equipotential, this is equipotential line, these two. This is the field. Okay. Quantity of water flowing through each flow channel is the same. True or false?
True, sir.
Yes, true. This is one of the assumption we take for construction of a flow net, that the discharge between any two particular flow line, that is through any flow channel, is equal. So this is true. Yes. Westergaard's influence factor is a function of,
Both of these.
yes, both of these. What is the formula for the Westergaard's influence factor?
1 upon pi q upon z square.
Whole to the power 3 by 2, isn't it? So here we have r, here we have z. So this factor is in a function of both r and z. Clear?
Yes, sir.
Yeah. Now I believe now is the time for the numericals. So those who have done the class of seepage analysis, there weren't any like common questions, right? You could like solve these questions of flow nets. Hello?
Yes, sir.
Yeah.
Yes, sir.
Okay. Okay. This question, have you solved it? Has anyone solved this question?
No, sir.
Why? This is with the Westergaard formula.
Sir, actually, in classes they are directly giving formulas, sir, not solving numerical.
We're not solving only formulas. Okay,
Sir,
so you first. Okay, we'll solve it step by step. You first tell me what is the formula for Westergaard circular load.
Q bracket 1 minus cos cube theta.
Just a moment. Yes, for circular load, what is the value?
Q bracket के अंदर 1 minus cos cube theta.
1 minus cos 2 theta. Have I given theta over here?
Angle between depth and radius.
Or can you find out theta from here? Or can you solve it using the UDL circular load formula? 1 minus 1 upon 1 plus a by eta z whole square whole to the power 3 by 2 whole to the power half. Which formula you will use over here? Yes, tell me. Hello.
Cos theta formula.
Yes, cos theta formula. Cos theta, right? What is theta then? If you are using the formula of cos theta, then what is theta?
Depth upon under root depth square plus radius.
Depth upon under root depth square plus radius square.
Yes, sir.
Okay. So you do it in that way. What is the answer you are getting? Just a moment. You told q into 1 minus cos cube theta, isn't it? Hello? Who was it?
Yes, sir.
What is the formula? Q into 1 minus cos cube theta. Cos theta whole cube.
Cos cube theta.
Cos cube theta. But I have mentioned over here Westergaard analysis. Westergaard, not Boussinesq. Cos cube theta is which analysis? Boussinesq or Westergaard? Cos cube theta is the analysis by Boussinesq. I am talking about Westergaard analysis. Is it clear?
Okay, sir.
Yeah, so according to according to Westergaard's formula, Westergaard's equation or theory, what is the formula for circular load? I believe this is the formula. Sigma z will be equals to, it is q, that is the load intensity, into 1 minus 1 minus 1 by 1 plus a by eta z, or I'll just write it like this, r by eta z whole square, and this before 1 minus this whole thing whole to the power basically yes, this one whole to the power 1 by 2. I take it. Okay, this is the formula. Now what is the value of eta? The formula for eta is root over of 1 minus 2 mu divided by 2 into 1 minus mu. 2 into 1 minus mu. Okay. Now mu I have told you to take it as 0. Okay. So this is 0. This is also 0. Right. So 1 by 2. So eta equals to root over of half. Is it clear? First find out eta. Could you find out eta? Hello? Can you follow the sum? Please speak up. Otherwise, I'll just continue.
No, sir.
Yes, sir, continue.
This is just finding out eta of this equation. Okay. This is the next part.
Huh? Carne male mas. Japanese chai shi tai. Tai mane ask time. Ne din saran tai din tai.
Please mute yourself. Someone is talking. Yes. So this is theta, right? This is eta you have got. So if you put the value of root over of half over here, what will you get? What will you get? You will get sigma z equals to q into 1 minus 1 divided by 1 plus 2 into r by z whole square whole to the power half. Isn't it? If you put eta over there, eta equals to root over of 1 by 2, you get this formula. 1 minus q into 1 minus 1 by 1 plus 2 into r by z whole square. Now, if it is a circular section, what we have to do? You have to subtract the entire load of the outer circle, subtract the entire load of the inner circle from the entire load of the outer circle, isn't it? So the formula will be, formula of stress will be sigma z will be equals to q is how much? Q is 160. 160 into 1 minus 1 divided by 1 plus 2 into what is r? R is, I think the outer one is 5, inner one is 3.75. Outer one is 5, depth is 4, 5 by 4 whole square, and this whole to the power half is the outer one minus again 160 into 1 minus 1 by 1 plus 2 into I think RI is 3.75. Yes, 3.75 divided by 4 whole square. This one whole to the power half. Is it clear? The formula and how am I getting it? Anyone? Any doubt?
No, sir.
Yes. So you try to find out the answer now. This is the formula.
Sir, 41.9.
41.9. I don't think so. I'll just check once. Wait.
Sixty-four, sir.
Just a moment. Huh? I'll do it once.
64.
Sir,
63.65. You do it correctly. I'm getting 17.57. And
yes,
what
sir.
is the answer?
17.56.
Yeah. 17.57 is the answer. Okay.
Yes,
Those
sir.
who have not got, please check it once again. The first part will be 81.22. Okay. The first part will be 81.22. And the second part will be, I believe, 63.65. 63.65 up in two decimal places rounded off. And the answer will be 17.57. Okay. In kilonewton per meter square. Okay.
Okay,
Is
sir.
it clear? Yeah. Okay. So next sum. This one. So I believe you have written down all the data and the diagram also, right? I'll just solve the question right now. Diagram you have done? Everyone diagram you have drawn?
Yes, sir.
Okay. So this, the thing which happens is this line, this phreatic line, the topmost flow line is a parabola, and the parabola has a directrix. This is the directrix, and the distance between the directrix and this point, this is called the focal distance. Okay, S. So here, just a minute. Yes.
Sir, is this formula correct? Small q is equal to k into h square minus small h square for finding the
Yes.
distance. The
Yes.
discharge is equal to k
Yes.
into
K into S. Yes.
k.
K into S. Okay. This is equal to K into S. Now, what we have to do? You have to first find out K. How will you find out K? To find out K using the formula what? Root over of Kx into Ky, right?
Yes, sir.
Kx into Ky. And if you do it, you will get how much? 3 into 10 to the power minus 7. You see 4.5 into 2, 9. 9 root over is 3. 3 into 10 to the power minus 7 meter per second. Now to find out S. To find out S, you need to first calculate the head difference, that is H. H is equals to how much? 58 is the height, isn't it? Minus the height of the freeboard, that is equals to 56.5 meter. Okay. Next, you have to find out D. Now this is 0.3 L. You do one thing. This, it might like what to say become clumsy or haphazard. You check one standard textbook. Okay, standard soil mechanics textbook. You will see you can find out the derivation of these formulas. Okay, I am just solving this
Yes.
right now. After I solve this, you immediately check one soil mechanics book. I will say BC Punmiya or Gopal Ranjan or anything. BC Punmiya will be what is a better one. I'll bring the sum from there only. So BC Punmiya you check and you just go through the derivation of this formula. Okay. So for finding out this focal distance, you need H and you need D. What is D? D is equals to 0.3 L. This is the entire distance. D is the entire distance. Okay, I'm showing you what is D. From C to F. Yes. So if this parabola is starting from here actually, okay. So from this point till here, this is D. And to find out D, we need to add each and every component. So first is this component, then is this component, then is the crest, then is the this particular component. So while calculating this horizontal component, you need the slope, upstream slope and downstream slope. So in this way, we can find out D like this: 0.3 L plus the upstream slope is 2.75 into 2.75 into it is 1.5 freeboard, okay, plus it is 6 meter, this is crest height, plus it is 2.5 into H, that is 58, the entire height 58, and I am calculating the entire height, that is this one, entire this one I'm calculating, then I have to subtract the drainage blanket, right? Because I have to calculate till here, till the beginning of the blanket. So after this, I will just subtract the drainage blanket. Okay. So you do this. What is the value of L? Isn't it? What is the value of L? L will be equal to, saying you, L will be equal to the beginning of the dam till the start point of the phreatic line. That is this is L, where the phreatic line is starting from the beginning of the dam, like here. So L will be equal to the slope, that is upstream slope 2.75 into, this is the actual height, that is actual head 56.5. That will be equal to, I think it is equals to 155.38. And putting this formula over here, you find out D. Find the value of D like this. L is 155.38 meter. Is it clear? How am I getting L? Is it clear? How am I getting L? Hello?
Yes, sir.
Okay, you find out D and tell me the answer.
So 91.739.
Yes, 91.74 I can write. Right? 91.74. Now you have to find out the focal distance S. So focal distance S is equals to, the formula is root over of D square plus H square outside root minus D. Find out. Find the value of S.
So this is root of d square plus h square.
Yes, root of D square plus A square minus D. What is the value of S?
16.
16. Very good. 16 is the focal distance. Right. Now you put over here, you have S, you have K. 16 into 3, how much? 48, right?
Yes, sir.
So Q will be equals to 48 into 10 ki power 10 to the power minus 7. Here I am considering meter cube
Per second.
per second,
Meter cube per second. Yes, sir.
meter cube per second per meter width, because I am not considering the weight, okay? Not the volume specifically. So meter cube per second per meter width, it is 48 into 10 ki power 7. Is this clear? So this is the just the methodology of the sum. You just check any standard textbook to see the derivation of this formula. Okay. Someone wants to go there? Yes. Okay. So this technique is clear, Shakir? Hello?
Yes, sir.
Yes. So you just check any standard textbook for the derivation part. Okay.
Yes, sir.
Next question. Have you solved this question?
No, sir.
Hey, you haven't solved any question, did I?
No, sir.
Any numerical?
Sir, actually, all questions they have not solved in videos, sir. Course videos.
Achha, so none of this question you have solved anywhere previously.
Yes, sir.
Okay, fine. So that means this session was very much important to you, right? Because
Yes, sir.
you learned so many sums. Okay. So okay, I start with
First answer is 0.318.
0.318. First answer, no, not the answer. You have to use the basic formula for the Westergaard's analysis. What is the basic formula for Westergaard analysis? See here, I had not written anything about mu. If something is not written, okay, for majority of soils, the mu, there is a Poisson's ratio. Take it as 0, okay, and the Westergaard's formula is sigma z equals to q load divided by, for point load, for concentrated load this is the formula, q divided by 2 pi, I think, yes, 2 pi eta square z square, 2 pi eta square z square, okay, 1 plus r by eta z whole square, r by eta z whole square, and this 1 plus part whole to the power 3 by 2. Someone has done it. Yes. So this is the formula. Okay. Now I have previously shown you the formula for eta, right? This is the formula for eta. When mu equal to 0, we get eta equals to root over of 1 by 2, isn't it? So here in this sum, if you put root over of 1 by 2, you get half over here. So this half and 2 gets cancelled. Again you put 1 by 2 over here, root over 1 by 2, you get half, and outside you get 2. So if you,
Sir, neta is 1 by 2, but it is neta square.
eta is root over of 1 by 2. Okay.
Oh,
See,
okay, yeah.
root over of 1 by 2. So here
Yes.
we are squaring it and cancelling with 2 over here. Here also 1 by
Yes, sir.
root over of 1 by 2 whole square means half. Outside we get 2 over here. Okay. So the formula we'll be using is sigma z equals to q divided by pi into z square bracket 1 plus 2 into r by z whole square whole to the power 3 by 2. Okay. Now for the first instance, depth 10 meter, right? Situated at the axis of loading. For the first instant, r equal to 0 and z equals to 10. Okay, you put these values over
Yes, sir.
here, and q is 200 kilonewton. Put this value over here and find out the stress in kN per meter square for the first instance. This is pi into z square over here. Simple thing, for the first instance r is equal to 0, so 2 into 0 0 1, that is, this entire thing is not required, just q by pi z square, simple.
Sir, Q value?
Q value is 200 kilonewton. Consider a load of 200 kilonewton acting.
Oh.
Both the cases Q is same. Found the answer? Simple thing, q by pi z square. What is the answer? Hello? first answer will be 0.64. Because 200, z is 10, 100, it is 2 and the numerator and pi in the denominator. So just calculate 2 divided by pi.
Pi. Yes, sir.
Yes, 0.64, right? And in the
Yes.
second case, put r equal to distance of 2 meter. Yes, r equals to 2 and depth z equals to 5 in this formula. So it will be q, that is 200 divided by pi into z square, that is 5, pi into 5 square, 1 plus 2 into r is 2, 2 by 5 whole square whole to the power 3 by 2.
Sir, 1 point.
Yes, 1 point, how much? Hello?
Sir, 1.21.
No, 1.68 I'm getting. 2 divided by 5 whole square into 2 plus 1 into the power 1.5.
Sir,
Yes.
n will put at root of 1 by 2.
N root over
Eta.
n is eta is not here only, no. So for both the parts mu equal to 0, eta equals to root over half. So half into 2 gets cancelled. So the formula only has pi and z square. There is no 2 and there is no eta.
Sir, inside this into 1 plus 2 divided by
No, I have
r.
written no outside 2. That means eta over is not here.
Oh, yes.
Okay. Eta was here, eta was equals to root over of half, root over of 1 by 2, whole square means half, half, it goes to the numerator, it becomes 2. So it is 1 plus 2 into r by z whole square. Do it. I think you will get the same answer as me, 1.68 kilonewton per meter square.
Yes, sir, 1.68.
Yes, good. So this is the Westergaard's formula. Next question was this one. I believe if you're not done it, this is a very simple thing. Transform width is original width into this ky by ks. I have said no, the horizontal dimensions, the velocity or k, everything gets transformed. When they get transformed, they are multiplied with this ratio root over of ky by kx. Okay, so this transformed width was given over here, original width was given over here. This is the anisotropy ratio. You have to just play with the numerator and the denominator and find this answer. Okay, just write it down. Is it clear that whenever there is an anisotropic soil that transformed with any property which will be transformed, it has to be multiplied by root over of ky by kx, this factor. Okay, for transformation into the corresponding anisotropic soil, sorry, isotropic soil. Is this clear, Shakir? Transform with hello. Yeah, is this clear? You have doubt, right?
No.
Okay. Have you finished writing this down?
Yes, sir.
Okay. Okay. So last sum was this one. Okay. And someone asked where is the value of k given, permeability coefficient given. So k you have to find out like this: k equals to 100 d10 square, d10 in centimeter. Okay. This is the empirical formula for k when it is not given to us. So using this formula, k equals to 100 into effective size whole square, you can find out the value of k. Now nd by nf you had equals to 2, nf by nd will be half, h is 3 meter given. So in this formula, you know this formula kh nf by nd, you can find out the value of q. Okay, only part is the k was not given over here, that you have to find it out. Is it clear, everyone? Is it clear, Shakir?
Yes, sir. You
Yeah.
want me to show it again?
Yeah. Do it. The second part you can do it on your own because you have done these sums. The first part only you just copy that k equals to 100 into d10 whole square, and then apply kh into nf by nd, get 1.5 into the power minus 4 meter cube per second per meter. Okay.
So at last it's Q by 1 or L.
Yes, q by 1, that is per meter width, that is we consider unit width, right?
Yes, sir.
Yes, per meter width, so it is 1.5 into 10 to the power 4 meter cube per second per meter width of the sample or the sheet
Yes,
pile,
sir.
whatever was given. Okay, clear?
Yes, sir.
Okay, so I believe we have written down all the answers, and now you have a clear idea. And whichever you don't have any idea, you can go through any standard soil mechanics textbook for the derivation of the same. Okay.
Okay, sir.
Yes. So okay. Next day it will be purely, not purely. It will be the discussion will be more inclined towards problem solving. Okay, numericals, because here you have some idea, you have some theoretical questions from stresses. In Bozeniak's theory, I'll be giving more numericals. Okay.
Yes, sir.
Okay. Okay then. Thank you everyone. Have a good evening. You can leave the meeting.